Today, our discussion is on design of LCL filter for a three-phase grid-connected inverter. First, we will look at why do we need a filter for grid-connected inverter. Without filter, the current generated by the grid-connected inverter is something which looks like this. It contains lots of harmonics. When we inject this kind of current into the grid, it deteriorates the grid voltage and hence causes lots of power quality issues. In order to avoid all these issues, we always keep a filter at the inverter output. So when we connect a filter, we will get very smooth sinusoidal current without any harmonics. This is the basic schematic of a three-phase grid-connected inverter. We have a DC voltage source at the input. I have marked it as VDC. These are the power electronics-based switches, which form the inverter bridge. We can use devices like MOSFET or IGBT as the switch. These inductors and capacitors forms the LCL filter. These are the inverter side inductors. I have marked it as L1. And these are the grid side inductors. I have marked it as L2. Capacitors, which are connected in star between the inductors. I have marked it as C. Finally, we connect the inverter to the grid. I have marked grid voltage as VG, and grid current as IG. I have also marked the pole voltages as VI. Now we need to find the transfer function between grid current and inverter voltage. For that we need to draw the circuit in the S domain. Here is the per phase equivalent circuit of the LCL filter in the S domain. I have marked all the values properly. Now apply KCL at point X. Then we get VI minus Vx divided by SL1 is equal to Ig plus Vx divided by 1 by SC. Mark it as equation 1. We can also write Vx as Ig into SL2. Mark it as equation 2. Solving equations 1 and 2, we get Ig by Vi is equal to 1 divided by S cube L1 L2C plus S into L1 plus L2. Let's substitute L1 plus L2 as L, and L1 L2 divided by L1 plus L2 as LP. Then we get Ig by Vi is equal to 1 divided by SL into 1 plus S squared CLP. This is the final transfer function equation. From this equation, the resonant frequency may be expressed as omega resonance is equal to 1 by root CLP. Now we start designing the filter values. First step is the selection of switching frequency. Based on device constraints, size and cost of components, and thermal consideration, you can select the desired value of switching frequency. Here, a switching frequency of 10 kHz is chosen. The second step is the selection of resonant frequency. Choose a resonant frequency that is well separated from both fundamental and switching frequency. As a thumb rule, we choose resonant frequency as switching frequency divided by 10. So we get 10 kHz divided by 10. That is 1000 Hz. The next step is finding the value of capacitance. The value of capacitance is chosen based on the reactive power requirement of the capacitor. As a thumb rule, reactive power absorbed by the capacitor limited to 5% of rated power. We know that reactive power can be written as Q is equal to V square divided by 1 by 2 pi FC. Now apply the 5% condition, then V square divided by 1 by 2 pi FC is equal to 5% of rated power. This can be rewritten as V square into 2 pi FC is equal to 5% of S. Therefore, C is equal to 0.05 into S divided by V square into 2 pi F. For a 100 kVA grid-connected inverter with 230 volt phase voltage at 50 Hz frequency, we can calculate the value of C as capacitance is equal to 0.05 into 100 kVA divided by 3, all divided by 230 square into 2 pi into 50. That is equal to 100.28 microfarad. Here I have divided the total power with 3 to get the power in a single phase. The final step is finding the value of inductance. For the design of the inductor, we need the transfer function that we are previously calculated. We know that resonant frequency is given by 1 by root CLP. Then, Ig by Vi can be written as 1 by SL into 1 plus S square divided by omega resonance square. At switching frequency, we can rewrite this equation as Ig by Vi at switching frequency is equal to 1 divided by j omega SWL into 1 plus j omega SW square by omega resonance square. Since j square is minus 1, and taking the magnitude of this equation, we will get Ig by Vi is equal to 1 by omega SWL into 1 minus omega SW square by omega resonance square. From this equation, we can write the value of inductance as 1 divided by omega SW into Ig by Vi into 1 minus omega SW square by omega resonance square. This is the final inductance equation. Now I will show you how to calculate L1 and L2 using this equation. Consider a 100 kVA 3-phase grid inverter with 230 phase voltage at 50 Hz. Then phase current is 100 kVA by 3, all divided by 230. That is 144.92 amps. We already have taken switching frequency as 10 kHz. And resonant frequency as 1000 Hz. As per IEEE standard, the value of grid current at switching frequency should only be 0.3%. So Ig at switching frequency is 0.003 into 144.92. That is 0.434. Now, for a sine triangular PWM scheme, minimum value of Vi at switching frequency is 0.9 times grid voltage. That is 0.9 into 230. 207 volt. Substituting all these values, we get inductance as 76.68 microhenries. Now L1 and L2 can be taken as L by 2. So L1 and L2 will be 38.38 microhenries each. These are the minimum value of the required inductance. The maximum value of inductance is calculated based on the voltage drop across it. Voltage drop is always limited to 20% of grid voltage. So Lmax is given by 0.2 into V grid divided by 2 pi into 50I. On substitution, we get inductance as 1 millihenry. Therefore L1 and L2 can be calculated as 1 millihenry divided by 2. That is 500 microhenries each. So this completes the design of LCL filter. Thanks for watching.